Good evening, everybody, and welcome to the Chicago Quantum Summit's Solving Unsolvable Quantums, the Future of Quantum Computing. My name is Ryan Mandelbaum. I'm a science writer at Gizmodo. So what is an unsolvable problem? It is not what is the meaning of life, and it is not why do I continue to tweet even though it causes me so much pain and anguish. But we're looking at sort of understanding the universe at the most intricate scales, what kinds of new materials or medicines might come about from this sort of new technology. So we've got a really awesome program tonight. It's going to start with a talk from Talia Gershon from IBM, and then we'll go into a panel. I'm just going to ask that you hold any questions off until the end of the panel. I know you're going to have a lot, but we just want to make sure that everything flows nicely. So to start, I'm going to introduce Talia. Talia Gershon is the Director of Research Strategy and Growth Initiatives at IBM Research. She received her PhD from Cambridge, developing thin film materials for solar energy applications, but she can explain quantum computing better than anybody, certainly better than me. So Talia, why don't you come up?
All right, thank you, Ryan, for the introduction, and it's a pleasure and an honor to be here talking to all of you about quantum computing. So I've got about 20 minutes. It's not a lot of time, but my hope is that I want to give you at least a small flavor for what quantum computing is, where we are, and how we got here. So I thought I'd start with how we got here, because it's a nice segue. So let's see if I can get my clicker to work. Clicker's not working. Oh, there we go. OK, so I'm trying to go back to the, there we go. All right, so rewind the clock about 100 years. Put yourself into the shoes of scientists in the early part of the 20th century. You have a model of the world, it's classical physics, and you continue to study nature and the universe. And you start to observe a couple of things that you really can't explain with your classical physics. So let's take a couple examples. First one is superposition, right? So imagine you're studying electrons, and you believe that these electrons can be either spin up or spin down. You start to observe that actually they're not always just either spin up or spin down. Sometimes you find them in some combination of spin up and spin down. So this was a really interesting and surprising observation. Other things that people discovered around that time, the uncertainty principle, this idea that particles sometimes behave like waves, waves sometimes behave like particles. Some really interesting things were observed. Fast forward a couple of years, the observation of entanglement. So this was also another surprising finding. So imagine you have your two electron system, and you believe that you can describe them each individually. I've got this electron, I can describe the properties of this one. I've got the second electron, I can describe the properties of that one totally independently. But you observe that actually you can do this thing where they're entangled, and suddenly you can't describe them independently anymore. Any operation you do on one of these electrons affects the whole system, right? So these observations that there's these things that are happening that you can't explain with classical theory, this was really the birth of quantum mechanics. Around the time, mid-1900s, there was also, huge innovation in the field of computing. Fundamentally, information theory, progress in computation around World War II, the invention of the microprocessor and beyond. So there was a lot of ideas and thinking around information theory itself. And around that time in the 60s, scientists like Charlie Bennett, who is still an IBM researcher and roams our halls today, started to ask the question, how can we think about the efficiency of computation? Can we actually use ideas from quantum mechanics to rethink information itself, to rethink processing information itself? So we went back and we found some really early writings from Charlie where he started to think about these ideas, and he wrote quantum information and then he scribbled it out as false, right? But these things, people were exploring these ideas and figuring things out. So this community began to form. In the 80s, 1981, there was this really famous conference that convened a lot of the big thinkers in this space. And it was a joint conference organized by MIT and IBM. And at that conference, they were exploring, okay, so we have these ideas around this quantum information theory. We think it's going to be more efficient for certain kinds of computations. What kinds of computations do we think it could be better at? And one idea came out was simulating nature, right? And there's a very famous quote from Richard Feynman from that conference where he said, nature isn't classical, damn it. So if you want to simulate nature, you better make it quantum mechanical. And so people started to think about, okay, well, that's a particular problem that's very hard to simulate on a conventional machine. We believe it could be done more efficiently on a quantum computer. In the 90s, a new idea came out. We think we can, Peter Shor published a famous algorithm where he said, I think we can actually factor numbers significantly more efficiently on a quantum computer. And this was a really big idea. So if you think about taking two large prime numbers and multiplying them together, that's a relatively easy computational task. But if you take that new number and you try to factor it back into the primes, that's a very hard problem, right? Because is it divisible by 2? Is it divisible by 3? And so on and so forth. So when Peter Shor published this new algorithm, it said, actually, no, we can factor numbers exponentially faster on a quantum computer. That was very, very exciting, right? And so new ideas kept coming out. We think this more efficient form of computation will be interesting for solving certain key problems. Then you got to say, well, I need a quantum computer if I'm going to do that, right? So towards the end of the 1900s, David DiVincenzo published a series of criteria. We said, okay, if we're really going to build a quantum computer, it has to have some fundamental properties, right? You need a carrier of the quantum information. Just like how with classical computing we have the bit, with quantum computing we need a quantum bit or a qubit. We need to be able to initialize these qubits in a ground state. We need to be able to control their properties and perform operations on them called gates, logic operations called gates. So he published a series of ideas that said, okay, if we're really going to build this, this is what it needs to be. In the, moving into the 2000s, we saw enormous progress in the experimental side of quantum computing, right? So in the early 2000s, we saw, NMR technologies being used to prove that you could factor 15 down into the primes 3 and 5, a demonstration. And then moving forward a few years were the invention of this new kind of qubit that's actually patterned on a processor, right? So this idea that now we're going to take a wafer, just like we took with classical machines, right? Classical computing is wafer-level devices. We're going to actually pattern qubits on silicon, right? In 2007 was the invention of the transmon qubit, which is the technology we use in IBM research for our quantum systems, and it's used by others as well. Fast forward a couple years, a lot of improvements in the technology, and in 2016, it was the first ever demonstration that we could put a real live quantum computer, not live, obviously, it's technology, a real quantum computer on the cloud, a 5-qubit machine that you could use, the operations that you need to do to actually program a quantum computer. So it was a 5-qubit system with a universal gate set that people anywhere in the world for free could access and interact with and run research experiments and explore and learn. Since that time, we've gone from having just one system on the cloud to having a fleet of 14 systems on the cloud. And the technology's advanced from 5 to 14 to 20 and even now 53 qubits that we have. So the technology has made enormous progress. This is the sort of thing that you can do now. You can log into an interface that looks like this. This is the IBM Q experience. You can log into an interface like this, and all of that quantum technology is just abstracted from you. You can go in and play around with these different kinds of gates and experiment with how they work. And you can click that little button that says run, and it sends a real experiment to a real quantum computer sitting in a lab in New York. It's kind of mind-boggling when you think about it. So what's actually behind the scenes, right? What's actually behind this? So we talked about the need for qubits. So this is a picture of an actual processor. These squares represent our qubits. These are those transmon qubits we talked about. And it's not microscopic. This is not an individual atom. This is a millimeter scale device, but it operates like an atom. So it has properties where you can put it into a superposition state. You can entangle the state of one qubit with another qubit. You have these squiggly lines that represent how qubits talk to each other and how they talk to the control system outside of how you do measurements and perform operations. And you have to cool the whole thing down. You see there 15 millikelvin. And the reason you have to make it so cold is not just because these systems are made from superconducting materials, but because any noise in the system will destroy your information. If you think about light, which is quantum mechanical, right? You don't want the light hitting your quantum processor. You want to shield the processor from as much noise as possible. So it lives all the way at the bottom of a dilution refrigerator. I'm clicking the button, but it's not advancing. It lives all the way at the bottom of a dilution refrigerator, which looks like this. So you have your chip that's in that can to the bottom right. It's inside of many layers of shielding. And you have to communicate with that processor, and we communicate through microwaves. You saw those resonators? You communicate with the chip through microwaves. And those microwaves come in down through those coaxial cables, those cables you see on the right. And it's controlled through a rack of electronics. So outside of the system, you'll have a rack of electronics, which is creating those microwaves that communicate to the processor, and then you have to close the whole thing up because room temperature is very far away from 15 millikelvin. So there's a lot of technology that goes into actually building and creating these systems. And if I click the next button, This is roughly how it works, right? So you have the job that you send from your machine to the quantum system, right? So you define, you see that interface roughly resembles the quantum experience. You send the thing you wanna do to the system. These are the microwaves that represent that operation you want it to perform on the chip. Those microwaves come into the chip through those resonators. They perform an operation on the qubits, and then you collect the information out back through the microwave electronics, and the answer is read out through your interface. So what kinds of problems do we believe that this can solve? I sort of alluded in the beginning to simulating nature is something we still believe these quantum systems will be very powerful to do. Problems like factoring I mentioned already, but we believe that other problems like optimization and machine learning, there's a huge opportunity to explore those applications on a quantum computer. And that doesn't mean that quantum computers are going to solve everything. They're not going to replace classical machines, right? You're still going to have a laptop, you're still going to have your smartphone, but now you're going to have access to computational power to solve certain kinds of problems you couldn't solve before. But it's definitely not true that everything will now be quantum. This is a device and a computational system for really hard problems. So what does it look like to actually simulate these things on a quantum computer? I talked about simulating nature, simulating chemistry. One thing you might want to do is calculate the bond length. So if you have two atoms and they're going to bond with each other, they're too far apart, the energy is higher than the equilibrium energy. If you push them too close, the energy also goes up. So there's some equilibrium bond length where there's a minimum in energy. And this is a result that we published a couple of years ago that showed how you would simulate these three different molecules on a quantum system. These are small molecules, right? So the straight line or the filled line represents what the actual calculation would be on a regular classical machine. And then the dots represent what answer you get if you simulate on a quantum computer. And you can see that there's some noise that makes the experimental results differ from the expected results. But what we showed a year later is that actually there can be techniques using the exact same hardware where you mitigate the errors, right? So using experimental techniques, if you understand the noise enough and you perform experiments where you kind of stretch the pulses, you can actually back calculate what your answer would have been on a non-noisy quantum system. So tons of innovation happening, not only in the algorithm side, but figuring out how we make the most use of these near-term devices. And we use techniques like error mitigation to improve our ability to get great results. So these noisy systems, you might ask, okay, well, are they actually going to be useful for doing meaningful things? So there was a proof that came out last year in 2018 where we showed that actually there's a mathematical proof that shows that yes, you can achieve quantum advantage. And by that I mean there's an advantage, a computational advantage for using a quantum computer. You would choose to do it because it's better. That it's actually mathematically possible to achieve quantum advantage even with these noisy machines. And shallow circuits is about having, okay, you can't have an infinitely long set of gates that you perform because the information will eventually decohere, but so if you restrict the number of gates you have, then you keep the circuit shallow, then you can do useful computation. So we're not the only ones advancing the field. That's a really important point. So we've got incredible research scientists. We have a very exciting research agenda, but just think about having 160,000 people all over the world accessing these devices and doing some really exciting things. So I wanted to spend a few minutes sharing some of the innovation that's come out of the community, leveraging these systems and really advancing the field, and just to make the point that there's a huge amount of innovation happening outside in the community, students all over the world really making a difference in the field. So the first thing is research. So research scientists, imagine a time you're a theoretical quantum information scientist. Imagine a time before you had access to a real machine. You would innovate, you'd create these algorithms, and then you had no way to test them on a real device, right? It used to be that experimentalists would build experimental systems, and they were the only ones who had access to them. And then theoreticians would build algorithms, and they never had access to a machine. And now there's a way, right, to bring these two worlds together and to make it so that theorists don't need to have access and build their own system. They can use one through the cloud. And there's been tons of really exciting research that's been published leveraging these systems, everything from studying entanglement, to studying new algorithms, to studying noise, to building new compilers, thinking about different ways of actually running algorithms on these machines. And a key enabler for this is an open source project we launched called Qiskit. We launched it in 2017, Quantum Information Software Kit, and I'll talk a little bit more about that in a bit. But huge amount of innovation in the research community, 200 papers in just 3 years. So that's really been very exciting to see. The second one is education. So think about, you're a student. Imagine you're in a computer science class and you don't have an actual computer, right? There's so much learning you do just by doing that having access now to an actual quantum computer in the classroom has made a tremendous difference. We've seen a lot of universities start to adopt actually real quantum computers in the classroom, assigning homework and problem sets and projects through this interface. There's tons of educational material out there, not just stuff that we've produced, but MIT has a course that Ike Chuang ran. We have a video series and a textbook that we've created. So tons of really exciting things that have been enabled through access to these kinds of systems. And then finally, you don't have to be someone who's studying quantum information science as a discipline. You can just be anyone with an interest, right? And you can have access to this. There's a huge community online of people who who talk to each other about quantum computing and Qiskit through Slack. There's been tens of millions of experiments run, and it's really anyone now. And I think that's very exciting. So like I said, we launched this quantum open source project, and it's been really fascinating to see the evolution of Qiskit. So Qiskit has 4 components. There's Qiskit Terra, which is down at the circuit level and at the gate level, and this is where some of that work on quantum compilers has been happening. There's Qiskit Aqua, which is a layer about algorithms. So what are some algorithms that we want to run on quantum systems, and can we define those in that layer? There's Qiskit Ignis, which is about error mitigation and techniques around how to deal with error in these systems. And then there's Qiskit Air, which is our simulators, right? So how can we simulate noise better? How can we simulate different kinds of noise? And really thinking about using that as a vehicle also for advancing the field. So I highly encourage and welcome all of you to go check it out. It's completely free and available, and there's lots of discussion groups and support online. And we've also been running hackathons, right? So lots of open source projects have a community of people that get together and they advance the field together. So these are just some of the things that we've seen recently come out of the community at these hackathons. One thing that was really exciting, and again, these are not people who studied necessarily quantum physics. Sometimes we've had developers come in. We've had high school students come in and participate in Qiskit hackathons. You can see that this team that won the hackathon, they integrated PyTorch with Qiskit. PyTorch is a very popular machine learning framework, so that was very cool and interesting to see. So the key message that I want to end on is basically that you don't have to think this is something that's inaccessible to you. You don't have to think that this is somebody else's innovation to drive. This is an open community. Tools are available to you. Resources are available to you. And it's an opportunity for you to engage and really advance the field. It's a very exciting time in the history of quantum computing. So thank you.
Awesome. That was great. Thank you.
Thank you.
So next up, we're going to have a little panel. We're going to bring on stage David O Salaam. David is the director of the Chicago Quantum Exchange. He is also a professor at the University of Chicago and a scientist, a senior scientist at Argonne National Lab. He's one of the leading researchers in spintronics and quantum information engineering, and his team sort of explores the weirdness of the small and the weird. And so he's going to help us understand this as well. Dave, why don't you come up on stage? So to get started, I think that we maybe need to take a step back and just ask, what are these machines actually going to do for us in this room? I mean, how is this going to affect my life? I'm very selfish.
Do you want to start?
No, I think
I've been talking for 20 minutes. I'll keep going.
Keep going.
So, there's a couple of things. I think, one of the things I think is particularly exciting about this moment is that there's a set of things that we believe with evidence that these machines will do. And then there's a whole host of things that we'll discover just by virtue of having them. If you think about the early days of computing, we had a machine and we knew what it would be useful for. In the early days, there were some ideas. But just think of everything people figured out they could do by virtue of having access to one of those machines. And I think that's a very exciting thing, right? All the innovation is going to happen just as people explore things. You saw some of the things that we're already looking at. How can we better simulate nature? And can we use that to understand matter better, maybe discover and invent new materials? And things like machine learning. These AI systems or machine learning systems, they're getting more complex. They're getting more computationally intensive, right? If you look at some of the most advanced AI algorithms out there and the models out there, they could take a long time to train, like weeks to train. So can we think about actually making that more efficient to allow us to get to even more complex systems, which can do even more? So those are just some ideas about where things might be going.
Yeah, I mean, I think your idea of, for example, trying to predict new materials with a quantum machine means the future could be incredibly exciting. You could think about room temperature superconductors. If you could design a material to create those, it would change everything from energy transmission, right, to levitating trains. And one of the problems of moving in that direction is it's hard to calculate the properties of these materials. So I think the most exciting thing in the field is we don't really know actually where we're going. We're going really, we say it's like driving on low beams, 100 miles an hour on the road. You're going really fast, but you don't really know where you're going.
But
and you're sort of hoping nobody's going to stop you.
And that's the power of letting people try things, right? Letting people explore. There's going to be so much discovery that happens just by virtue of exploration.
So it's sort of just any industry that could, use these optimization algorithms, machine learning. I mean, it sounds like pharmaceuticals, material science, energy, pretty much anything that touches our lives.
I can tell you about a couple companies in particular that we know are excited about this. So a couple of years ago, IBM launched something called the IBM Q Network. There's about 80 organizations spanning academia, national labs, and companies in various industries. There's JP Chase is in there, so obviously some enthusiasm about discovering applications for finance. Samsung is in there, Mitsubishi Chemical, right? So there really is a lot of interest in fast movers in some of these industries to say, I want to be the first, right? I want to have the first advantage.
Well, but I think it's also because the technology that's used to build quantum machines can also be used for other things beyond computing, like communication and sensing. So these qubits that IBM has worked so well to protect from the world, you could flip them around and say, well, don't protect them, expose them. And they're extraordinary sensors. So for medical imaging, right, for putting quantum sensors in living cells, watching information move, these are things that are happening right now. So I think it's already going to impact our life.
So why don't we get into that a little bit more then? So, I mean, what are some of the places, of these quantum technologies that we ignore when we're talking just about quantum computing? I mean, can you get into maybe some of the communications aspects and things like that?
Yeah, so I mean, you mentioned JP and Chase. I think a lot of us are worried about our information security. I am. And it'd be great if I was going to be able to send you a message using a protocol that would prevent eavesdropping. So one of the great things that you mentioned, for example, about these quantum states is the act of looking at them changes it. So you have built-in security just with the laws of quantum physics, and building a global network with complete security would change the way we think about sharing information, right, and protecting things. And I think for sensing, things like understanding proteins in us. Today it's hard to understand more than 1% of the proteins in our bodies because you have to come up with a way to crystallize them and take them to a machine to explore them and then argue at science meetings about what you're looking at. It's a lot of fun, it pays the rent. But at the end of the day, it's not what you want, right? You want a tool that could look at any arbitrary protein and get the structure-function relationship to understand how we work and how pharmaceuticals work. Quantum sensors, in principle, there's a pathway to doing that. And I would argue if these qubits could be used for quantum sensing at that level, it would revolutionize areas of biology and chemistry.
And I mean, how is that going to integrate into sort of the processor? I mean, is there sort of a quantum landscape that you're envisioning in the future with a whole quantum infrastructure?
I think there's so many, maybe this is again a comment for David because maybe it's closer to your area, but there's so many challenges that you'd have to get past. Like we talked about the fact that, all the things about you want to sense one thing, but not other, you don't want anything else from the environment probably to influence that measurement. Some of these technologies are like trapped ions. How do you have a trapped ion that you can control and put out in the world as a sensor? I think some of the technologies that you would have to invent for quantum sensing are probably different in some respects.
I think that's right. And I think you're right. You want to build an ecosystem where quantum states are moved all around without ever seeing the classical world. So you'd like the sensors, the communication, the quantum computer, all to be moving this around. There are a lot of challenges. And the great thing about research, of course, is unlike you, where you actually have to do something useful. We don't really, the stockholders we have are all of you. So thank you for your taxes, by the way. But that means we can actually reap the benefits of accidental discoveries. And I think a lot of the things that you've been mentioning have come out of real surprises in this field, like the sensing.
Yeah.
So it seems like there's a ton of promise, this sort of like whole future we can envision, but today, I would like to know where we actually are. I mean, I just heard this announcement of quantum supremacy, and it sounded weird and scary, so I would love to know what was actually going on there.
Okay, I'll start with kind of two observations about that, and then David,
No,
obviously. So observation one is just language, right? We got to be careful about what language we use because there's a very clear and deliberate misinformation about what that is. The name quantum supremacy actually originated when it was a small insular quantum information community, and they all knew what it meant amongst themselves. They named an experiment and they named it quantum supremacy. And the intent was never to communicate to the outside world what we all interpret it to be. If I tell you I have this thing and I have quantum supremacy, it's like quantum computers taking over the world and like, infiltrating your home and all this crazy stuff. It's like it's not what it is. And it doesn't even really mean yet that there's a machine that does something meaningful and useful that we can't do today with regular machines. So we got to be really careful about the language we use to talk about it. And we got to avoid the hype. Right? So I think this whole field struggles with some hype, especially when you have language like that. Making claims that you can do a thing that would take 10,000 years to do. It just turns out that there was no reason to say 10,000 years. We did an experiment where we ran that same thing in 2.5 days. We published the paper on it. So there's no reason to hype. There's no reason to sort of be deliberate about misinformation. So that's number one. Number two is really about how we define progress in the field. So in my opinion, we should be measuring progress in the field by how are we making progress towards solving those meaningful problems. I mean, from my perspective, one of the things that's so exciting about this field is we really believe it will be useful for meaningful problems. So we should be measuring our progress towards that. So where we are, back to your question, where we are is that you saw some of our demonstrations that, not just us, there's lots of people doing really outstanding science. We're at the place where we're taking those meaningful problems and we're demonstrating slow and steady progress towards solving them. We are not yet, nobody, this is not us, not anybody, has yet demonstrated that they have a machine that can solve meaningful problems better than others, but we believe that over the coming few years, we will be crossing a threshold into really, over the next maybe couple of years, we'll start to see that quantum advantage that I talked about, which is the ability to demonstrate that you can do useful computation better than without a quantum computer, that somebody would choose to use a quantum computer because it offers you an advantage.
Yeah, I agree with all of that. I mean, the language is terrible.
Yeah. Yeah.
That's my short answer to that.
It's misleading.
I don't have to sell anything to anyone. But quantum advantage means something. I mean, which really means meaningful problems. What can you do? I do think there's a value for large companies saying something like this, even if it's not entirely correct. But it sets a point that people can start to probe. So when a company comes out and says, we've done it, there are a lot of assumptions to make that true. And to get thousands of people now looking at it and examining it and maybe debunking parts of it, right? And it's a way to start focusing the field. And I think there's some value to that. But I agree with you. I think we're not there. I think we will be there. And it's very important not to exaggerate. I mean, that's the first thing that will kill science fields, is to claim or push things faster than reality. Because the reality is this field's going really fast, really well.
Already.
Already.
And it's so exciting, and there's no reason to exaggerate it because the actual truth is very exciting.
Yeah, I mean, for example, here in Illinois, the national labs are funding a program to teleport information between over a 30-mile distance. That's going to happen shortly. And just to be able to build a platform to teleport particles, not people, just so we're clear. To have thought about that even a decade ago was unthinkable, right? And the fact that you can literally do it today is extraordinary. So we don't need that. You're absolutely right.
So it's almost like we're in a place where quantum technology is real. It exists. Right. It is starting to get to a point where we're starting to explore what its applications might be, but not necessarily a point where it's actually doing those applications, or certainly not beating things. But we can start to actually envision them, and it's real.
Yeah, I think it's very much like saying we're at the vacuum tube stage in quantum technology. I'm guessing some people here don't know about vacuum tubes, but they are like really big, useless transistors. And there were things you could do with that, right? From building radios to doing microwave electronics, and then things became scalable and things really accelerated. And I think we're just at that stage, and it's a little dangerous to predict. Mm-hmm.
And so now, just kind of bringing it back to where we are today, there are a lot of different technologies that are coming about. Specifically, there's different architectures for quantum computing. Would you be able to sort of compare what exists today? And I know that there's a trapped ion quantum computer, superconducting. I would love to know the difference and what we can expect to see from them.
Okay, so the technology we use is a superconducting transmon qubit, which we talked about. There's all of them have their trade-offs, right? So if you think about how do we envision, there's a lot of things we have to care about. How easy is it and quick is it to actually send signals in and out and actually do operations and get the information back? You have to care about how scalable is it? How many can I fit, and how can I arrange them, and how can I build larger and larger systems? Coherence times, right? How long is my coherence time? That's really a measure of how long my information will last that I can do useful computation. And a lot of these systems have their trade-offs, right? So the technology we chose, we felt had the best trade-off, but others, for example, the ions have longer coherence times. They're a little bit slower to probe, right? So anything?
Yeah, and I would say, for example, technology that's the farthest behind, which is of course what we work on, it's the least useful right now, is seeing if we could take the $1 trillion of semiconductor technology that's driving a lot of our economy today and use it to build a quantum machine. It's a challenge. It's very hard to do this. But if you can do that, and then there's one's patient enough to make it work, then you'll have a scalable technology. And that's the key, making billions of quantum states where you really could build extraordinary machines. This artist's rendition that's on the wall around us, I'm staring at it, came from one of the articles our students did a number of years ago to show you could move the quantum state from one electron, which is that green dot on the wall, into the core of the atom, one nuclear spin, come back later and extract it. So it was a subatomic quantum memory. It worked really unreliably and not very well. It worked about a third of the time, which for physicists is fantastic. For IBM, not so good. But scientifically, it showed there's no barrier for building subatomic memories and making literally, in that memory, you can store billions of variables fine. But to do it enough to make something useful, not so much. So I think exploring all of these material platforms, atoms, superconductors, semiconductors. Intel has now launched a semiconductor program, for example, for quantum states because they want to use their fabs, right, to think of can you make it scalable. And they're working with Delft in the Netherlands and other places to really push that. And it's beginning to work at a few bits now.
So they can already make silicon stuff. So now they're going to make silicon quantum computers.
Well, you said it.
They might. Well, the talk is called The Future of Quantum Computing, so I would love to talk about, what are some of the next major milestones? Maybe let's start with what IBM is working on, and then, how are we going to get to this quantum future where we actually have quantum technology as part of our lives?
So this kind of goes back to the question of how we measure progress. So we talked about progress towards useful problems. There's another unit of progress that we've been documenting for ourselves, and we've been exploring it with the community, is this idea of quantum volume. So frequently when we talk about quantum computing, we talk about number of qubits. But actually, you could pattern an infinite number of qubits. Not an infinite. You could pattern a lot of qubits on a chip. But the problem is you can't control them all together reliably with all of those nice properties of being able to entangle states and control the whole thing. So it's really about making progress towards not only the number of qubits, but how good a job you're doing at controlling them appropriately. So how much can you minimize errors? How well can you actually get operations on multiple qubits at once? So we've kind of taken a lot of these parameters that have to do with building quantum systems where you can actually make meaningful computations. We've rolled that into a single parameter called quantum volume. So really, we have a roadmap for quantum volume. We've seen a lot of progress in quantum volume over the last few years. We want to continue that progress. And if we do, then again, we believe that in the coming years, we'll be able to demonstrate a meaningful quantum advantage where somebody would choose to use a quantum computer to solve a problem because they can solve it better. And it's not just a quantum computer, to just add to that. It's this partnership between classical and quantum systems, right? There's a classical computer controlling the quantum computer, right? So it's really about getting these systems to work well together.
Yeah, and I think it's important to remember it's a global enterprise, right? It's not just in the United States. So, for example, a few years ago, China's both announcement and demonstration of using a satellite, right, to link quantum ground stations 1,200 kilometers apart. It's extraordinary to think about building a global network of quantum systems that you wire together. But I think one of the real challenges for progress will be the workforce. So particularly for a lot of people in this room, and when you talk to the 70-odd companies, right, in the Quantum Economic Development Consortium, and you ask them what's their big concern, what do they worry about with progress? The first thing they all say is the workforce. Where will quantum engineers come from? And when you look back at the formation of the electronics industry, that's what drove it. Electrical engineers, right, microwave engineers, radar, that, I think, will actually limit the progress, believe it or not. I think it's going to be the workforce.
Well, so how are we going to sort of develop this quantum infrastructure and workforce to actually push things forward?
So, I mean, I believe, and we're already probably starting to see it, is that a lot of the ideas that are behind the scenes of these quantum computers are probably already making their way into curricula. Like, if you think about it, I took a class that was extremely memorable when I was an undergrad in material science, and it was a class about electronic, optical, and magnetic materials and devices. And it taught me everything about lasers and diodes and transistors and photovoltaics and magnetic hard drives, every device you could imagine. I'll bet that class, if it was taught today, would include qubit technologies, right? So we're going to start to see this is a technology that's going to become extremely important. That's just going to infiltrate a lot of curricula, right? So that's, I think, one. And then I think we're also going to see, as the industry grows and there's a demand for the skills, I think that will also drive, the curricula and the student interest too.
I think that's all true. I think that's right. It's hard, one of the things in this field that's going to be challenging is to get computer scientists thinking about quantum machines. Anybody here a computer scientist? Okay, then I can say this. That's great. I mean, one of the tricky things about getting computer science into quantum engineering is, for example, one curriculum that traditionally doesn't teach quantum mechanics. And why should it, right? It's different. But you will need this for quantum technology. And, it's a challenge to, say, take a graduating student who's offered a lucrative job at IBM or Facebook or LinkedIn and say, well, or you could work on a machine that doesn't really exist the way you want, and it's not clear where it's going, but you should work there.
But we are starting to see programs emerge that are quantum computer science programs. And in fact, we've hired amazing people out of those programs. So they're emerging.
Absolutely.
And we are also seeing that there's an opportunity for people who've developed really deep skills in one place to reapply those skills in this place. There's a bunch of people who are part of our HPC supercomputing team that are now working with our quantum researchers, right? Because simulating is a big deal. But
I think we're going to need to get the help of, say, high school teachers. I mean, somehow this is going to have to be conveyed at a much earlier level than people heading the job market. And that's a society challenge, which I'm sure we'll do, by the way. But we need to figure out a good way to do that.
But it's interesting because and sorry if you have other questions, but this is an interesting topic.
I can tell you that it's pretty amazing that we're getting physicists to code, because I'm a labs physicist, and physicists are the worst coders. No offense, physicists. We don't.
But just think about, and probably some of you can relate, and I don't know if maybe you've always loved quantum mechanics, but I think a lot of people who take quantum mechanics in college, they don't see the applicability.
Well, that's because it's taught terribly.
Could be. But when you study a discipline and you don't see the practical application, it's very hard to get excited and motivated about it. And I think now, with all of these exciting applications, people can get way more excited when they take, Introduction to Quantum Mechanics. They know that there's something meaningful that can be done with it from an engineering perspective.
Actually, I think it's a really good point. I mean, I even know when I was taking quantum mechanics, really? That's all? Just a few minutes left? Okay. When I was taking quantum mechanics, you're taking relativistic quantum mechanics, you think, why the hell am I taking this?
Yeah.
It's completely useless. But now you realize, in fact, it's not, right? And it's an incredibly important part of this emerging technology. So I think you're right. I think that's going to change the discipline quite a bit.
Well, so how is sort of academia and business and the government working together to actually see this through and make it actually happen?
This is a great one for you about the National Quantum Initiative. Maybe you could talk about that.
Yeah, so a lot of us in this room were engaged in building the National Quantum Initiative, which was signed into law at the end of last year, which is a $1 billion initiative to get the US going in building an infrastructure for quantum science and technology. It's fantastically important because it gets universities and companies working together on joint efforts with some significant goals. So I think the United States it's been a bipartisan effort, something that I personally never seem to read about. But I know we're not supposed to talk about that, but it is something that people agree on that is so important that we just have to move forward. So I think that's a really good step.
Yeah, and I think the point you made earlier, there's a huge opportunity for different parts of our, our ecosystem to focus on different things. Like David talked a lot about some of the really exploratory work his team is doing.
That's a nice way.
Which has to happen. We need to be doing that exploratory work. We need national labs to be setting those benchmarks, right? We need to be engaging and defining what are these measurements that we're going to use to track our progress. We need industry to be focused around what business value can we create and the whole startup ecosystem. So I think there's a lot of room for different players to play a different important role.
And I mean, mentioning the national labs, particularly here in Illinois, is a good point.
Yeah.
I mean, the requirements for this technology are unparalleled historically.
Yeah.
You need to build circuits where you can place individual atoms where you want, deterministically, which means by design. How do you even know you've done it? You need some sort of microscope to look at something at the atomic scale, which often means you need a synchrotron. Places like here at Argonne, at Stanford, which are billion-dollar microscopes, right, that the national government has built for all sorts of studies. And so getting companies to work with these systems, look at what they've made, right, go iterate back and forth, you need all of this infrastructure to push this forward. I mean, it's a good point.
Can you now just envision for me, it's 40 years from now, the ultimate quantum computer, the universal fault-tolerant quantum computer exists. So the quantum technology and communications have advanced, that it's actually in production. What are you most excited to see? What are you doing right now with it, and why are you excited about it?
So this may not satisfy you as an answer, but I think it's true, right? So we benefit from technological innovations every day without thinking about them. Just imagine the scale of engineering and technology that went into the creation of a smartphone. You don't, ever. Nobody ever thinks about that. But that's decades, years of innovation that has enabled us to have a different quality of life. So I think that the technology is going to progress, and it's going to change people's quality of life, and it's going to be behind the scenes of some really important improvements in the way we live. That's my 2 cents on that. Yeah.
Yeah, I would echo that, and also echo the fact that you'll be disappointed with any answer that I give. Because every time you try and predict the future, you're inevitably wrong.
Yeah.
But there's no question it's going to impact the way we live. When you think about having small bits of matter that can store more information than atoms in the observable universe, which quantum systems can do, it will change a lot of things in the way we deal with technology. And I think the exciting part is we really don't know yet.
To be fair, backstage, David did say he envisioned a caffeine molecule that was 10,000 times more potent.
I did say that. Thank you for sharing that with the room, by the way.
It was good. That's what I was hoping you'd say. So I think that it's probably time we just get to audience questions. I'm sure that some of you are burning with questions. We'll just start with you in the front, and then I'll work my way back.
One of the things I've noticed is I started out a long time ago at the University of Illinois in a totally different discipline and got into a computer course, which it seems to be the stage we're at right now. Well,
Hello. Okay. Right now, as we push the speed through traditional linear computers that operate so rapidly, we call it multitasking because we do a lot of switching. It seems the weak link right now in quantum will be the error correction that is normally built into any one of our computers right now. And it says, I didn't drop the mic. The thing that is the weak link right now, it seems, in the whole system is the fact that we're doing traditional linear to just gather the data and control the system. What kind of work possibly is being done on the error correction, or I don't know what the term might be, normalization of the data that you were talking about, just to get it into a compliant format for us to actually look at? If we've got anything working with quantums to do that function.
Yeah, I'd love to hear about error correction as well.
I think there's actually 2 parts to the question. So part 1 is about a little bit more about how the computation works. And I just want a quick clarification there. So quantum computers are not doing exactly the same series of operations that classical computers do, but faster. Actually, each operation on a quantum computer is slower. The key is that it does the computation in a fundamentally different way and more efficiently. So just to give you an analogy, what a regular machine will do, like you said, maybe you can parallelize it, but there's a sequence of operations that have to be performed kind of 1 bit at a time if you get down to the lowest level. Because you have to describe each bit individually, and you have to address each bit individually. But what quantum computers are going to do is actually create a whole system, and the information about the problem and then the processing you do to manipulate that state is happening on the whole system.
My understanding is that normally if you have a traditional computer, it's like putting a mouse in the maze and he's trying all the examples, whereas quantum is you're standing above the experiment and you're just looking down and you're going, oh, there it is.
They're basically what you're doing at the end of the day is you're creating a quantum state. You're physically creating a quantum state on a processor, right? You're manipulating a series of qubits to create a quantum state. And then what you have to do is you have to take the problem you want to solve and encode parts of it into that quantum state, right? And now the algorithm, as the algorithm continues, you're manipulating that whole quantum state. And at the end, the final state represents the solution. That's probably how you should think about it. And that's not the same thing as I'm going to do all the same operations in the same order. So that's part one. And then part two is about error correction. So you're totally right that error correction is a fundamentally different thing in quantum systems, because in classical information, you can just make a copy of the information, and then you can check both and say, do they agree or do they not agree? If they don't agree, you had an error somewhere, right? You can't make copies of the quantum information. So there's been tons of innovation to try to figure out how do we actually correct for errors. There's a long-term plan, which is the millions of fault-tolerant, millions of qubits fault-tolerant. They call them error correction codes. There's a way where you put extra qubits, and those qubits help you kind of essentially remove the errors and the noise from the systems, and then you have the computational qubits. Then there's the near-term devices, right? The noisy intermediate scale quantum computers, and that's where we are now. And I shared with you some techniques that we have that allow you an idea that that we shared at APS March meeting, I think last year, was you could stretch the pulses, right? So we talked about microwaves come in, they manipulate the quantum state, something comes out. Maybe there's errors there, but if you make the pulses worse, you repeat it multiple times, each time getting a little bit worse, you can actually back calculate what your answer would have looked like without noise. So there's these mitigation techniques that we're looking at to try to use near-term noisy quantum computers, and those are slightly different schemes than the sort of long-term plan. Any other?
Yeah, I mean, I think we should maybe deal with some other questions, but just to say that basically your question is incredibly important, because what limits the scaling of quantum machines is dealing with the errors. And the errors scale in a horrible way. It gets harder and harder as you add more and more of these quantum bits. So at the end of the day, that's the biggest challenge.
Next question. We'll take somebody from the middle back, that guy all the way in the back.
Is there a way we can turn the lights on here? So we
Oh, sure, that would be
Can we
great.
turn the lights up so we can see people? Or maybe not.
Hello. Also on the topic of error correction, today Ivanka Trump tweeted, "It's official, explosion emoji. The US has achieved quantum supremacy."
This is what I'm talking about.
So I just wanted to ask if you could correct her a little bit, because maybe you should scale down that statement. Because I was thinking maybe it would be more appropriate to say, we demonstrated quantum supremacy, but now that I've heard you speak, I think it's even less than that. So
This is exactly the point I was making about hype and language, because the words, they sound like they mean the thing, but they don't, right? And it's very dangerous for people to misinterpret where we are, right?
And they claimed, the Trump administration claimed credit for this.
So many things wrong with this.
I think
Can
we
you
should move on.
can you
All right, next
generate
question.
some headlines about by correcting her, like what is real?
Well, we talked about where we are, right? We talked about where we are, which is we're at a stage where we have systems that are getting sufficiently sophisticated that we want to be able to apply them towards meaningful problems. Nobody has yet proven that they can achieve an advantage for solving meaningful problems in a way classical machines can't. Nobody. So the truth is that we're making progress, right? And we talked about some of the progress, and we'll continue to see progress. And we should be measuring progress in units of how well are we doing at moving in a direction of being able to solve meaningful problems.
So I would say there are a lot of tweets that come from the East Coast that you may not pay much attention to.
Google,
What was really achieved?
They solved one very specific, rather contrived problem, and claims that the problem was solved in 200 seconds, the way that a supercomputer would solve it in 10,000 years. Now, there's a lot of people who've already refuted that statement or have published papers that sort of maybe have dialed it back, but it's just one very specific. They claim the first time that a quantum computer has beaten a supercomputer at anything. Now, whether that's true or not remains to be seen, but it's just basically means it's not that. It's not worth like the tweeting explosion emoji.
Because it sounds like a weapons race. That is in the intelligence field or the geopolitical field. The main thing is to get quantum technology to break each other's encryption.
Well, I think one of the reasons people are interested and governments are interested is because, as Talia used this nice example about factoring prime numbers, the mathematics that's used for factoring prime numbers and dealing with it was the basis of today's encryption schemes. So when you go onto Amazon and you buy something with your Visa card, and you see the lock symbol appear, your number is encrypted. right? And it's based on the fact that there isn't a technology today that can decrypt that number on the timescale of your transaction. So it's secure. If a technology that were to come into play that could do that, factoring the numbers and extracting your original number, it would be a risk to the current financial system, right? And that means banks transferring just, yeah, that's why JP Morgan's interested, safely moving money around, just ordinary things. So that encryption is important just for the security of your own information, and that is something, as you said, quantum machines aren't good at a lot of things, in fact, many things. A calculator at Walgreens will do pretty well compared to a quantum machine. But what quantum machines are exceptionally good at is factoring.
And one just additional thing to mention there is not today's quantum computers, right? The ability to do that meaningful factoring for numbers of sufficiently interesting size, you do need large fault-tolerant quantum computers, and I'm talking on the order of multiple millions of qubits, right? So we're still pretty far from that, at least known algorithms.
And that's why this whole idea of building a scalable system is so important,
right?
Because if you can end up building millions, then it is something you need to think about.
Awesome. So I love all of these questions. I just want to make sure to get as many questions in that we keep it to one sentence and one question, if you don't mind. You've been...
First of all, thank you for a really enjoyable discussion. And my question is about that workforce problem. So I'm like in programming in computer science environment, and when I speak to people and I say them like I'm working in quantum information science, and they are really excited about that. So there is really a big interest among programmers, among like classical programmers, into that field. But the sad thing about that, they think that they're dumb, so they can't understand the physics. And even sadder, think they're probably true, because quantum physics is really complicated, and once you are trying to comprehend all these concepts, you inevitably will feel dumb. And the first question is whether to be quantum programmer, do you need to comprehend all those complex like Feynman path integrals, all that stuff, or you probably don't need to dig that deep? And if you do, how do you find time for people to study all that stuff? Because it really takes time.
Okay, so there's three things I want to say about that. Number one, I want to talk about the computer scientists in our team working on quantum computing, right? Did they have a background in it before they started? No, they did not, right? So we have teams of software engineers that help deal with everything in the quantum stack, everything from the low-level hardware. What is the software stack that takes you up to the place that you can write algorithms and they compile on the quantum machine, right? So there's tons of people in the team that had no background in quantum computing when they came in, and they're making really important, meaningful contributions, right? And they're behind that Qiskit project, right? They're really deeply integrated in that. That's number one. Number two is we've seen people all the way from like early in their computer science degree contribute meaningfully to Qiskit without having ever had anything to do. This is outside of our team, having any background whatsoever in quantum, and they didn't have to. They created some really interesting compiler innovations. So it's about optimizing. You have gates, and you want to compile them on an actual machine. There's a compiler. And there's optimization problems in there, and you don't have to know a lot about quantum information to do that. There's a need for people in all kinds of places. And then the third thing I wanted to say was we've been running these Qiskit hackathons. So we had one in Madrid last year, and tons of people showed up, and they all had the exact same concern. Oh, I don't know anything about quantum computing. Am I going to be able to do anything? And every single team delivered some really cool project at the end, and they were all really excited to have been able to do something meaningful. It'd be great to have like a mentor help you come up to speed, but it's not beyond the reach of computer scientists today. That's my 2 cents.
Awesome.
Developing technology for running quantum computers is one thing, and writing quantum programs, developing quantum algorithms is another.
Correct. That's different, right? So if you want to create new algorithms, like sure, you have to know something about quantum information. You have to study it, right? Just like anything, right?
I want to get to a couple more questions, if that's okay. Sorry. All right, next up. Yeah, right there.
So I just ask a quick question. So you said quantum computing is very good at simulating nature. What is your definition of nature? And I know it's very good at simulating like chemical particles, but is there like a greater scope of definition of nature?
Yeah, so an oversimplification is to say that to simulate a quantum system on a classical computer is really inefficient, right? But to simulate a quantum system on a quantum system, there's a transformation. You can describe the quantum state you want to simulate like this. You can describe the quantum state you're going to create like that, and there's a transformation, right? So it's actually a lot more efficient to simulate quantum systems on a quantum system.
But maybe one example that maybe would help answer your question is something like photosynthesis. So that's something we see today, right? But you could argue it would be nice to simulate that exactly on a quantum machine to understand how light is turned into energy through a chemical process, right? And how nature stores energy. This is something you could simulate perfectly on a quantum machine. And by learning how that's done, it could lead to new ways to store energy.
Yep, right there.
Yeah, so traditionally we've used tools like logic, gates, and math to take advantage of bits and bytes. For qubits, are those the right tools to use?
We believe they are, right? So we talked about the David DiVincenzo criteria. You need some carrier of the information, and then you need some way by which you can manipulate them to process information, right? So there's a different set of gates. They're not the same gates that you had for classical information. There's a different set of gates. There's a Hadamard gate that's used to, to initiate superpositions. There's like different kinds of gates, qubit rotations, right? They're not the same kind of gates, but you need a gate set that you use, and you create these circuits that are part of the algorithm computation.
Closer, yeah.
A lot of the applications of quantum computing that we have heard are all high level, where like you need, it's like big problems like drugs and materials discovery. So I was just wondering, would there ever come a point where quantum computing would be like cost efficient in the sense, you have a huge dilution fridge and I'm sure like that's for big applications, that's fine. But do you think there's a thrust going towards making things which are a little more, I guess, economically accessible?
I love that question.
I'm answering all of them. If you want to weigh in here.
I like that.
The question was whether quantum would ever be cost competitive, and the kinds of problems that. Go ahead, David. I've been talking too much.
Are we ever going to see a quantum iPhone and it's going to be in my pocket?
It'll be in your head. Your head, not mine. It depends what you mean by cost efficient. I mean, when you think about the approach of exascale computers, for example, for really significant supercomputers, and you look at the energy they consume, right? Next generation machines will take up to maybe 40 to 50 megawatts of power just to run the computer. So there alone, I would argue, just on energy concerns, quantum calculations will really help. Is that what you were thinking?
That's the idea. And as David said, you're never going to use it for 2 + 2, right? So that's not the kind of problem that we're comparing cost effectiveness.
So unfortunately, our time is up. I appreciate all of these awesome questions. And thank you again, everybody, for coming. Thanks again, Talia and David, for coming and answering questions.
Thank you.